Welcome to Video 2 for this unit on exponents and scientific notation. In this video, we're going to focus on more exponent rules. When we multiply a positive power of 10 by 1/10, the exponent decreases by 1. Take a look at this example. 10 to the 8th power multiplied by 1/10 is 10 to the 7th power. This is true for any positive power of 10. We can reason in a similar way that multiplying by two factors that are 1/10 decreases the exponent by 2. That means we can extend the rules to use negative exponents if we make 10 to the negative second power equal 1/10 to the second power, or 1 over 10 to the second power. More generally, the exponent rules we have developed are true for any integers n and m if we make 10 to the negative n power equal to 1/10 to the nth power, which equals 1 over 10 to the nth power. Here is an example of extending the rule that 10 to the nth power divided by 10 to the mth power equals 10 to the power of n minus m to use negative exponents. 10 to the third power divided by 10 to the fifth power is equal to 10 to the 3 minus 5, or 10 to the negative second power. To see why, notice that 10 to the fifth power can be rewritten as 10 to the third power times 10 to the second power. This expression can be rewritten like this. So the original expression is equivalent to 1 divided by 10 to the second power, or 10 to the negative second power. Here is an example of extending the rule that 10 to the mth power raised to the nth power is 10 to the power of m times n to use negative exponents. 10 to the negative second power raised to the third power can be found by multiplying the exponents. 10 to the power of negative 2 times 3, or 10 to the negative 6th power. To see why, notice that 10 to the negative second power equals 1/10 times 1/10. Using this, we see that 10 to the negative second power to the third power is the same as 10 to the negative 6th power. So far, we have focused on powers of 10 because 10 plays a special role in the decimal number system. But the exponent rules that we developed for 10 also work for other bases. For example, if 2 to the 0 power equals 1, and 2 to the negative nth power equals 1 over 2 to the nth power, then these equations are true for any exponents m and n. These rules also work for powers of numbers less than 1. For example, 1/3 to the second power equals 1/3 times 1/3, and 1/3 to the fourth power equals 1/3 times 1/3 times 1/3 times 1/3. We can also check that 1/3 to the second power times 1/3 to the fourth power equals 1/3 to the power of 2 plus 4, or 1/3 to the 6th power. These rules for multiplying and dividing expressions with exponents only work when the expressions have the same base. How do we combine expressions with the same exponent but different bases? Consider 2 to the third power times 5 to the third power. We can rewrite this as 2 times 2 times 2 times 5 times 5 times 5. Regrouping this as 3 groups of 2 times 5, shows that 2 to the third power times 5 to the third power is equal to the quantity 2 times 5 to the third power, or 10 to the third power. Notice that the 2 and 5 could be replaced with different numbers or even variables. For example, if a and b are variables, then a to the third power times b to the third power is equal to the quantity a times b to the third power. More generally, for a positive number n, we can write that a to the nth power times b to the nth power as the quantity a times b to the nth power, since each side has exactly n factors that are a and n factors that are b. In summary, we have found rules to help us keep track of repeated factors when using exponents. Using variables such as x, n, and m, where x is any positive number, can help us see the structure. We also extended these rules to make sense of negative exponents as repeated factors of the reciprocal of the base. Here, x and 1 over x are reciprocals. And lastly, we defined any positive number to the power of 0 as 1. Thank you for watching video 2 of 4 for this unit on exponents and scientific notation.